Hey kids, can't ever go along without talking about the fundamental theorem of calculus, right? It is fundamental. So we've been doing a bunch of stuff with looking at the graph of the derivative, realizing that if you had the accumulator function, right, using the accumulator function, that the graph you were accumulating integrals under was the derivative, right, which comes from this theorem. If little f is continuous, then the accumulator function has a derivative at every point. Remember, little f doesn't itself have to be differentiable. The graph of little f, it just has to be continuous. If little f is continuous, remember, little f is the derivative of capital F. And if little f is continuous, it means that capital F has a derivative at every point on that interval. And then further, derivatives and antiderivatives undo one another. Remember, this integral sign and this little differential of t, that is the antiderivative notation. D over dx is the derivative notation. So when you have capital F as an accumulator function and then you take its derivative, the derivative notation goes away and just f drops out, and then you can put x back because you don't need the dummy variable anymore. And again, it is just the same as if you had x, right, f of t, right? If you had x and somebody cubed it and then cube rooted it, the inverse operators go away and you're just left with x. That's exactly what's happening here. Notice if you have the derivative of an integral, and remember an integral is really and synonym for that is antiderivative. The derivative of an antiderivative, that's what I have right here. And here. That's all part of the antiderivative and derivative notation. If you have the derivative of an antiderivative, and the derivative variables match, the variable of differentiation and the variable of the upper limit of integration, if they match, and the lower limit of integration is a constant, then if you are asked to take the derivative of an antiderivative, all you have to do is copy the integrand over and replace the dummy variable with x. We copy it over, copy paste, replace the t with an x. So look at this problem. Evaluate. There are some people that might try to actually anti-differentiate and then differentiate. Stop it. Recognize that you have derivatives and antiderivatives together. The lower limit of integration is a constant. The upper limit of integration matches the variable of differentiation. Copy and paste. 1 over 1 plus x squared. Do I have the derivative of an integral? Check. Does the derivative variable match the upper limit of integration? Check. Is the lower limit of integration a constant? Check. Boom. Done and done. That multiple choice answer takes me 0.2 seconds, and it saves me time for a harder multiple choice problem. Question should be, what happens if everything doesn't work out so nicely? So look at this problem. I do have the derivative of an antiderivative. but the upper limit of integration does not match. It's an x, right? And that's not what I mean by match. Like I'm not going to change variables on you, but it's not exactly the same. The upper limit of integration is a function in terms of x. It's not just x to the first. Well, you are taking a derivative. And what you're taking a derivative, it's really a composition. What's been put in place of x has been x squared. So you just need to remember, I told you it never goes away, the chain rule. So I still have the derivative of the antiderivative. I still have the lower limit is a constant. So I'm going to copy the integrand over, right? Here's the integrand, copy, paste. In for t, I put x squared, but I have to spit. What do I have to spit? Spit the derivative of x squared. So I actually get cosine x squared times 2x, which if that was multiple choice, somebody would write the 2x first. Whoa. Okay, so mental note. If the upper limit of integration is not just x, I've got to use the chain rule because you are taking a derivative of a composition. In place of x, x squared has been shoved. And every time you take a derivative of a composition, you need to use the chain rule. So what's going on here? Do you have the derivative of an antiderivative? Check. Does the variable of differentiation exactly match the variable inside the integral? Or as a bound? It does, but what's wrong? The x is in the wrong place. The lower limit of integration is not a constant, but the upper limit is. Hey, what are you going to do if you really, 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 really want that 5 on the bottom? Negatize, baby. So in order to use the fundamental theorem, it is a theorem. You cannot mess with it. You have to use it as it is stated and as it has been proven. You've got the derivative of the, oh, I forgot my green box over here. You have everything in my green box is going to disappear. I have my constant at the bottom. I have my variable on the top, and I don't have a composition. It is just x, but I had to negate my answer in order to get x to the top. Now notice I have a t 2 different places. I am going to copy over the integrand. 3t sine t, but in place of t, I'm putting the x, and I don't have to use the chain rule because there's no composition, it is just x. But I do have to negatize because the original problem had x in the wrong position. Uh-oh. I do have the derivative of an antiderivative, but neither limit of integration is a constant. Boo! I'm gonna cry. Well, remember what we talked about integrals, property of integrals, right? As long as little f is continuous, and it is, there's nothing that would break this up. Right? The denominator will never be 0 because e to the t is always positive, and then you're adding 2. So the denominator will never be negative. So this little f is continuous. Therefore, I can split up the integral anywhere I want. X squared has a domain of all real numbers. 2x has a domain of all real numbers. 1 over 2 plus e to the x has a domain of all real numbers. If I'm going to split up the domain, where would you like to split it up? 0. So notice what I have here. I have 2x to 0, check, and 0 to x squared. Do you see how that connects? Now, I know I don't want to throw you by the fact that I wrote it in a different order, but that is just a sum, so I can write it in any order. Let me go back and let me do the precursor step. I want to split this up, and I want to split it up at 0. Right? 0 and 0. Well, actually, that's the same way, silly. If I start at 2x and stop at 0, and then add going from 0 to x squared, that is the same by the properties of integrals of going from 2x to x squared, right? That's what I did here. And all I did was change the order. Do you see why I would want to change the order? I don't have to, but this first one with 0, a constant on the bottom, matches my theorem directly. But I am going to have to chain rule here because I have a composition. However, look at this one. This one I don't have my constant here. But what do we just show that we can do? Right? I'm going to negatize this piece and flip it around. I could have absolutely left it in this order. I just didn't like to lead with a negative, that's all. And again, it does not matter the constant we use as long as the constant is in the domain of the integrand, and 0 is in the domain. So here I go. I didn't do anything to the first one. I left it alone, but remembering that I'm going to have to chain rule here. But notice my plus has been turned to a minus because I need to reverse the limits of integration because I need my constant on the bottom. I'm going to have to chain rule here because this is a composition. I have to chain rule every time I don't just have x. So there I go. The derivative of the antiderivative dropped out the integrand. I replaced the t with x squared, and I spit out the derivative of x squared. I copied over the minus. I still have the derivative of the antiderivative. So I copied over the integrand. I replaced t this time with 2x, and I spit out the derivative of 2x. I am not going to clean it up any more than that. Okay, so you have a bunch of book problems like these examples that I've given you. And this one is the nastiest one, where you do have to remember that you have to actually split it apart and remember that one of them is going to be negated. You can use whatever whatever constant you want because you are taking the derivative. And what is the derivative of any constant? 0. Right? I mean, this isn't this function, but I was just showing you. It doesn't even matter if the constant you use is between your value. It just doesn't matter, right? If you're integrating from 2 to 6, I could say I'm going from 2 to 4 plus 4 to 6, but that's also equal to 0 to 6, right? Plus 0 plus 2 to 0 going the other way, right? There's just so many things I could do. So here's a couple more examples. You might want to pause the video and see if you can do them without me. I wanted to make sure to show you this notation because you don't have the derivative right in front of the antiderivative stuff. It just says capital X is an accumulator. What's the derivative? You have to say to yourself, constant. You are taking a derivative of an antiderivative. So you can just copy and paste the integrand, replace t with x squared. Since it wasn't just x, you must spit out the derivative of x squared. Here's capital F as an accumulator. You want to take the derivative of an accumulator. So a derivative of an antiderivative. I've got a constant down here. I'm going to have to chain rule this because it's not just x. Copy over the integrand. Replace t with 2x plus 1. spit out the derivative of 2x plus 1. I have an accumulator, but I'm taking the derivative of an accumulator, so the derivative of an antiderivative will make that go away. I can just copy over the integrand. Uh-oh, I can't yet just replace t. I can't replace it with 5. What has to be up here, right? I have to turn this around. How do I turn it around? What do I have to do? Negatize. Now I can put x cubed here, but what do I have to multiply by? The derivative of 3x cubed. Okay? Look at this one. F is an accumulator. You're taking the derivative of an antiderivative, which means you can just copy over the integrand. But instead of t, what are you going to put? 4x, which gets squared. And, good, multiply by the derivative of 4x. Right? Not the derivative of 16x squared, the derivative of what you put in, right? Put in 4x, spit out the derivative of 4x. What is this asking? Oh, this is just practice taking a derivative, right? So that's, all of this is to the 1/2. So 2 times 3 plus cosine of 16x squared to the negative 1/2 times the derivative of the middle. Well, the derivative of 3 is 0. The derivative of cosine is negative sine 16x squared times the derivative of 16x squared. Clean that up. Cool? All right, here are some, just like, you know, when we look at the AP test, we always are looking for problems that, right, oh, we never showed kids a problem like this before. And like, we teach you the math. There's no new topics that you haven't seen when you sit for that AP exam, but there will be some twists. So when we see twists, we like to give you out. They're going to come up with more twists, right? And different ones, but we'd like to expose you to all the twists that we can. So here was a new twist we've seen in the last couple of years. Write a function in the form accumulator. Accumulator plus some constant. C is a constant. That satisfies the given condition. The derivative of y is this. Okay, so here's y. Y is an accumulator. The derivative of y is e to the x tangent x. And they want me to write a function in the form. They want my equation to be an accumulator. So I'm going to write y is equal to okay. Now, what is it that they want? Here are the things I don't know. Where does the accumulator start? And what the heck is this c? Well, look at the information they gave you. They're saying that when x was 8, y was 0. Well, what's true about an accumulator that has 0? I mean, that is 0. Do you know any accumulators that are 0? How do you get an accumulator that equals 0? What do? Right? right? If x is 8, whoops, sorry, that's going to be 0. What are you going to put on with that? Where is my problem like this? Oh, there it is, sorry. Right? Isn't it true that you want this to be an 8 and I'll get 0? So remember, I have to, so if this starts at 8 and I just leave this alone, isn't it true that when you plug in 8 for x, 8 to 8 is going to give me a 0? I add 0 and I will get 0. Isn't that true? Right? So I kind of like reverse engineered this problem. So can you try this one? Look at this one. Again, here's y. The derivative of y is this thing. Oh, I guess I should have, sorry. Right? I'm going to put, this is the derivative. The derivative gets copied into here. But what about this one? So they want me to write y is equal to something to x of 3 minus cosine, got to use my dummy, so I don't know what goes in this space, and I don't know where to start the accumulator. But I do know that they're telling me that when I put in -3 for x, when I put -3 into here, they want y to be 4. So in other words, they want 4 to be equal to they want that to be equal to 4. Oh, plus something though, right? Well, again, how do you get this integrand to equal 0? How do you get the integral? How do you get the integral to equal 0? If x is equal, if you're going to stop at -3, make this 0. Start it at -3. So if you start your accumulator at -3 and go to -3, you know that the integral part would be 0. Well, you want this to be 4. So what are you going to do? Right? Isn't that true? Sweet. Find the linearization. You know what linearization means, I hope. Linearization is just a fancy way of writing the equation of a tangent line. Somebody asks you to write the equation of a tangent line, you do this. Go find an x. Where's the x in the problem? What's the y? Well, the y is, what is f of 0? So put 0 in for x. Going from 0 to 0 makes this whole integrand 0. 0 plus 4 is 4. How do you find the slope? What's the D word for slope? Derivative. So you need to take f and find what is f prime at 0. F prime, what is the derivative of a sum? It's the sum of the derivatives. What's the derivative of 4? 0. What is the derivative of the antiderivative? The integrand, lower limit was a constant, upper limit was x. So what is this? 0 plus ln of 0 plus 1 is 0 plus ln 1, but what is ln 1? So f prime of 0 is 0, which means my tangent line is y equals 4. And if you want to be super fancy, you can say linearization of x is 4. You don't have to, though. You could leave your answer like this, and it would be fine. Lame, but fine. So what about this one? Find f of 2 if the little f. Find little f of 2 if I have an accumulator of little f as the integrand is equal to this expression. So wait a second. These two things are equal, and I want to be able to plug 2 into the expression for f. I don't have an expression for f. This square root of x squared plus 5 is not little f. Little f has an integral on it. How do you get rid of an integral? Differentiate, right? You want to peel the integral off of little f. So take the derivative of this side and take the derivative of this side. The derivative of an antiderivative goes away. Copy over the integrand. Constant on the bottom, just x in the top. The derivative of x squared plus 5 is bring down the 1/2. Copy over the middle. Subtract 1 from the exponent. Spit out the derivative of the inside. That's f of x. Now they want to know f of 2. Bam, baby. Four plus 5 is 9. Square root of 9 is 3. Yeah, it is. Yeah, it is. All right. I will see you in our next live session.